4.5, tension. Well, if you pull a string, pull a rope, that's exerting a force. The rope will pull back on you, and we call that a tension force in the rope. So it's not so much the interaction between the surface directly, but the forces that are transmitted through strings to pull objects or hang them from the ceiling. We call those forces tensions. And the symbol for a tension force is Ft, like that. Okay? And we also get Ft, like Ft1 and Ft2 if we have multiple tensions in there. We ignore the mass of the actual strings for us and assume that the value of the tension in the string is uniform throughout the whole length of it. So it's really just setting up free body diagrams, and then in some cases a whole lot of setting forces equal to each other and solving equations. So here's an example. Say we had a ceiling like this, and then it went down to a 5 kilogram block hanging from that ceiling, and then another 5 kilogram block hanging below that one. We could ask ourselves, what's the tension in the ropes in a couple of different spots? Let's look at one right here. We'll do the free body diagram for that. Well, we would have a weight force down. Remember, we call those Fg. And then we'd have the tension upward. We'll call that Ft1. Okay? Now, what is the weight force? Well, it's equal to mg, right? The mass times acceleration due to gravity. And the total mass hanging below that, at that point, is 10 kilograms, isn't it, that hangs below? So times 10 meters per second squared, that would be 100 newtons. And it's directed down. So we might write it as minus 100 newtons. And then the tension here would have to balance that because it's in equilibrium. So that when you say something is in equilibrium, we say the sum of the forces is 0. So Ft1 must also be 100 newtons, the tension in there. Let's take a point in this rope right here. Well, I just moved it down a little bit, but that's the same. In that case, Fg is going to be a bit smaller, and the tension is going to be a bit smaller as well, going up like that. And so Fg is equal to mg, but the only thing below it is 5 kilograms at this point. 10 meters per second squared, and that's going down, so that's minus 50 newtons. And we can call this Ft2, so that Ft2 must be 50 newtons, like that, to balance it. So that's pretty simple. You just look at the weight below it causing the tension in the rope. But when they're at an angle, it gets a little more challenging. So let's say we have a ceiling and a sine, and that sine, now this, I know the sine is larger, but we treat it as like a point mass for the sake of us, so that all these tensions throughout are the same. So let's say some store has their sign up. We could call it, let's see, like Um, thinking of someone's, how about Jack's jerky, okay, like beef jerky being sold, and let's say that it had one tension here, and this is up at an angle of 30 degrees, and then another one at an angle of 50 degrees, like that. And the mass of this Jack's jerky sign is 100 kilograms. Well, let's look at the free body diagram on this, okay? First off, we're going to have down FG, okay? And we're going to have force of tension 1, and we're going to have force of tension 2. So there's our free body diagram. Now, because it's in equilibrium, the sum of the forces in the x direction have to equal 0, and the sum of the forces in the y direction, or any direction, equals 0. Okay? Now, that's important because for each of these tension forces at an angle, we're going to find the x part, which I'm just going to simplify now and call T1x, and leave the f out because I don't want, it's going to have so many, if it's ft1x, it's getting a little much, so I'm just trying to make it a little easier. That's T1y. This is 50 degrees over here, so we'll call that T2x and T2y. Okay? Oops. So, because the sum of the forces in the x are equal, we can see that that tells us that the only forces we have are T1x must equal T2x. Right? And and the forces in the y are also equal, so that gives us T1y plus T2y going up should equal our FG going down. That comes from these two equations right here, written out with what forces we have in the x and what forces we have in the y. T1x, though, is Ft1 times the cosine of 30 degrees. And that would equal T2x, which is Ft2 times the cosine of 50 degrees. So let's simplify that and find the cosine of 30 and the cosine of 50. Cosine of 30 is 0.87. So this is Ft1 0.87. And the cosine of 50 is 0.64. So Ft2 0.64. Okay, good. Now over here, T1y is actually Ft1 sine of 30, and T2y is Ft2 sine of 50, and Fg is mg So we can plug in the M is actually 100 kilograms times 10 meters per second squared. So that's 1,000 newtons. Sine of 30 is 0.5. So we have Ft1 times 0.5 plus Ft2 times the sine of 50, which is 0.77. So we have two equations and two unknowns. And we're looking for the tensions in the rope, Ft1 and Ft2. So now what you could do is you could solve this equation for Ft1. Ft1 would be Ft2 over the 0.87. We'll just divide it over. And 0.64 divided by 0.87 is 0.74. So Ft1 equals 0.74 times Ft2. Now that can get plugged in here for Ft1. So 0.74 Ft2 times 0.5 plus Ft2 0.77 equals 1,000 newtons. 0.5 times 0.74 is 0.37 Ft2 plus 0.77 Ft2 equals 1,000 newtons. 0.77 plus 0.37 is 1.14 Ft2 is 1,000 newtons. 1,000 divided by 1.14 is 877 newtons. And now once you have Ft2, you can bring it back over here, and Ft1 is 0.74 times 877 newtons, or 649 newtons. So you have the tensions in the two strings, ropes for the sign. So that's kind of a challenge, really. I mean, and we'll have to look at a number of examples, and we'll practice those in class to get better and better with it.